Here's a misconception. Temperature is not how hot something feels. It's how fast particles are moving and vibrating back and forth, and this changes everything. So first, what is kinetic theory? Imagine a box of gas, and this box of gas has billions of tiny particles inside. They move randomly in every direction all the time, colliding with the walls, and every collision pushes. That is pressure. So pressure comes from collisions. So when a particle hits a wall, it changes momentum. Newton's second law says that force is equal to the rate of momentum change. So how fast the momentum changes is equal to the force. And if you add up millions of these collisions and these momentum changes every time a collision happens, every single second, this creates pressure that's actually noticeable. This is the real source of pressure. It's not volume being squeezed, but it's motion hitting the walls. Next, let me show you the kinetic theory core equation, which is also on the free cheat sheet in the description. From kinetic theory, we get P, pressure, equals 1/3 density and VRMS squared. What's this weird value? What's velocity RMS? It means velocity root mean squared speed. So basically the effective average speed of the particles. In English, what this equation tells us is that faster motion equals more pressure. And here's the key. Temperature is equal to energy, because the average kinetic energy per particle equals 3/2 K times temperature, with this being the Boltzmann constant that we looked at in the previous video. You see that? Temperature. Temperature is equal to the average kinetic energy per particle. So temperature is not actually heat, it's the energy of motion inside each particle itself. This is why cold things move slower at the particle level, and why hot gases expand, because their molecules are hammering the container harder. Here's a bonus equation. You can find the speed of the particles by rearranging that previous equation for this. So speed of each particle is root 3kT over mass, with this being the mass of one molecule. Not the mass of one mole, but the mass of one molecule. So the lighter the molecules, the faster they move at the same temperature. Let's go through some problems to make some sense of all these formulas. First problem is, how much energy does one particle hold? And we're going to use kinetic theory to calculate the average kinetic energy of one gas molecule at a given temperature. The situation is this. You have a sealed glass tube, it's sealed off, and inside is oxygen gas contained at 350 Kelvin. You want to find how much kinetic energy each individual oxygen molecules carries on average as it bounces around in here. The Boltzmann constant, for reference, we'll write it up here as 1.38 times 10 to the power of negative 23. And of course, everything we need is on the cheat sheet in the description. But the solving strategy is just as important. You can't just know every formula and understand, but it does help. So the goal of the problem is to find how much kinetic energy our molecules have. So we'll use that exact formula. The average kinetic energy equals 3/2 Boltzmann constant times temperature in Kelvin. Let's plug everything we know in, which is the Boltzmann constant and our temperature, 350, given here. This is roughly 7.25 times 10 to the power of negative 21 joules of kinetic energy on average per oxygen molecule. Second problem, we're going to compare the average speed of helium and oxygen molecules at the same temperature. So once again, you have a container. Let's make it more interesting this time. It's a cube container. It holds a mixture of helium and oxygen molecules all mixed up. And this gas is held at 300 Kelvin. You want to compare how fast the molecules are moving, so the difference in speed. Let's find the speed of both individually. So which formula gives us speed for each molecule? It's this one that we looked at. Velocity equals 3kT over m. The molar mass of helium is 4 grams per mole, and the molar mass of oxygen is 32 grams per mole, depending on the conditions. So the mass per molecule, you can find the strategies we talked about in the previous video, which is giving us 6.64 times 10 to the power of negative 27 kilos. And for oxygen, 5.32 times 10 to the power of negative 26 kilograms of mass. These are some fat numbers. We don't need to calculate each velocity one by one. We can actually use a ratio. we know that the velocity of the helium divided by the velocity of the oxygen is equal to the mass of the oxygen divided by the mass of the helium over root. How did we get this ratio? How do we get this comparison? Because when you compare two gases at the exact same temperature, that means this 3 kT part will cancel out. So what we're left with is this. But I don't want to waste your time here. Just understand this is how we compare when the temperatures are the same. Notice how oxygen mass is on top and helium is on the bottom because heavier gas moves slower. Step by step, if we plug in our values for mass, which are up here, then we get answer as root 8.01, roughly 2.83. What does this number mean? It means that the helium molecules moves 2.8 times faster than oxygen when the temperature is the same. By the way, ideal gas laws like this and stuff like, all the stuff we've been looking at in this video, it all holds true 99% of the time. It's valid for 99% of problems that you encounter. But in real life gases, the particles usually attract and condense and bounce off wildly and have different speeds. That's when you get things like phase changes and triple points. But for majority of the time, this is fine. And it's all you need.